Hi everyone, my name is Martin Leroux and I'm a senior software developer at Kinova. Today I want to introduce the Kinova Kortex platform. Over the course of the next videos, we will go over specifics of how you can leverage the different features of Kortex to implement and improve your own robotics applications. But for now, let's focus on a top-level overview. The Kortex platform is the bedrock of Kinova's third generation of products. It's a shared software architecture that provides us as developers and you as users the possibility to develop and deploy projects on different robotic platforms without the trouble of adapting our work to different interfaces, communication protocols, control loop frequencies, and other inconvenient things. In other words, it means that when Kinova develops a cool new features for one of its robots, it automatically becomes available to the other Cortex-enabled robot models as long as the required hardware is available on said model. It also means that projects and demonstrations that you develop using a Gen 3 Lite, for example, can be deployed using a Gen 3 or even possibly future Kinova products. The Kortex platform is also powering Kinova's automation operating system, called AOS, a software platform designed to help manage the interaction between multiple robots, external machinery, and even monitor plant activities. We will go into more detail about AOS in a future video. At its heart, the goal for the Kortex platform is to make our robots indistinguishable from each other software-wise. All the algorithms are shared between the different robot models. In the case of the kinematics, for example, our numerical algorithm parses the information of a URDF file, a file format commonly used by ROS users to describe the geometrical and dynamical parameters of a robot, to be able to compute solutions without having to resort to manually derived solutions. Kortex also handles all the communication between the internal devices and between the robot and the outside world, through either the API or GPIOs. Speaking of the Kortex API, this is where, as a user, you come in to implement your robotic solutions. Where other robot manufacturers are very rigid with what kind of interactions, application, and customization is possible with their robots, the Kortex API has a completely open architecture. If you want to change the direction of the gravity relative to your robot, you can. If you want to send torque commands instead of position commands, you can. If you want to change the gains on the actuator control loops or even make your own control loop, you can. If you can think about it, odds are that the Kortex API allows you to do it. The way this is accomplished is that each device on the robot is associated with services that provide remote procedure calls, generally abbreviated to RPCs, enabling you to interact with it. There are three different kinds of RPCs. High-level commands are used to control the behavior of the robot as a system. For example, gripper pause command. These commands require a lot of additional computation, like limit validation and kinematics, so their call rate should be limited below 25 Hz. On the other hand, low-level cyclic commands completely bypass the base controller to send directly to their respective devices at a rate of 1 kHz. Finally, configuration RPCs allow you to customize the behavior of each device. Because the complexity of the configuration varies a lot between the different parameters, certain require more time to be processed, so their call rate should be limited below 40 Hz. So, how does it work? Let's examine what happens when you send the command to the robot. The command can be sent either from a user program, the Kinova web app, or a ROS node. But remember, they all communicate with the robot through the API, so if you know a feature exists in one of these interfaces, then it's also available from the others. A router program inside the base controller receives the RPC and forwards it to the appropriate device. For example, let's say we send a high-level reach post command. Then, the internal controller will use our control library to compute the kinematics and command to be sent to the actuators. When actuators receive commands, they reply through the cyclic data with the feedback from their sensors. Then, the actuator's internal control loop, running at 1 kHz, computes the electrical signal to send to the motor. Finally, the motor turns and the robot moves. This concludes today's video about the Kortex platform. Stay on the lookout for our upcoming video series where we will learn how to interact with Kortex robots through the web app, in a user program, and using Rust nodes.